Okay, good morning, everybody. We are hosting a special session this morning for the AIMS educational activity, and we're calling it the ST2110 Launchpad. So there'll be a series of 5 speakers. I'll be your first speaker, and I'll be talking about some of the basics of ST2110. Now, this isn't meant to be a highly technical presentation, but it is meant to give you a flavor for what the technology is about, why we're doing it, and some of the benefits and reasons why ST2110 makes sense in a modern network. So the first thing, what are some of the key requirements for an IP video system? Well, one thing you need is an encapsulation method. You need a way to put your data into IP packets. And in 2110, we use several standards that you see listed here. If you don't know what those are, we will explain those shortly. Synchronization. We need a way to align media streams to a common clock and possibly more importantly, align them to each other so we can synchronize video and audio and all those other good things. Switching and routing. We need to get packets from a source to a destination or multiple destinations. And we're going to use multicasting for that in many, many cases. And then finally, connection management. We need a way to tell devices that they're supposed to receive certain streams and for those devices to alert the network that those devices need the streams and that the network should provide those streams to those devices. And we'll do that using session description protocol, which is a way to describe streams, as well as NMOS, which is a way to communicate that information about sources to multiple destinations. So, let's just give you a big overview. An IP video ecosystem. This could be a typical broadcaster network. You might have some incoming signals on the left. You have outgoing signals on the right. In the middle, you see a large IP switch that is connected using many of the standards we're going to be talking about. We'll talk about ST2110, we'll talk about 2022-6, we'll mention some of these other things in passing. But if you look at it in a whole, everything on this network is capable of running over an IP network. So it's a unified system, and more importantly, everything flows over the same functional network hardware. So I'm not going to go through this whole evolution of IP media. We've been doing this for almost 30 years now, starting out with Pro MPEG COP3 back in the 90s. But you can see that all these signals have built upon each other. The technology has moved forward. You see some on the left that are compressed, many on the right that are uncompressed. You can see that sometimes we move from one side to the other. If you'll notice at the top, ST2022-7, that isn't even really specifically tied to any form of media. That is a way to provide redundancy. Now, the key thing about this diagram that I want you to understand, not only has it evolved over time, but all of these signals could flow on the same IP network backbone at the same time. You don't have to have one network for one type of media. You don't have to have an audio router. You don't need a video router. You don't need something special for metadata or control. Every single thing could flow over literally the same network. That's one of the real powerful things of an IP media-based system. We don't have to build separate infrastructure for separate types of signals. So, one of the stepping stones into 2110 was SMPTE ST2022-6. That was specifically designed for transporting SDI signals over IP. And just a few of them, standard def, 1080i, 1080p, 720p, those signals go very nicely in 2022-6. 2022-6 carries the entire SDI stream intact. Every single bit of that SDI stream is carried inside the IP packet stream. So video, any audio that's embedded in there, any ancillary data, the full horizontal ancillary space, the full vertical ancillary space, any signaling bits, any parity bits, everything is entirely packed into one packet stream. So you can deliver a bit-for-bit copy of the signal across your IP network. One of the things that is really nice about 2022-6 is that it has a companion standard called ST2022-5, and that provides forward error correction so that you can correct packets that are missing and you can add them back into the stream at your receiver without any loss. So very, very handy. If you don't know what a UDP port is, don't worry about it. It's not critical. So let's just take a look at a diagram of how this is put together. Let's try to bend that a little bit. So you take the entire SDI stream, including your audio, your embedded signal data, you put it all into one stream, you packetize that, you send those packets over your IP network. At the far end, you can depacketize it. You get back your SDI stream, and if you want, you can de-embed your audio, de-embed your ancillary data, everything else like that. And it's basically working like an existing SDI system. It's plumbing for SDI. It's easy to maintain audio and video synchronization because they're all in the same packet stream. There's nothing to interfere with them. But it's hard to process just one part of the stream. If you want to analyze audio, if you want to just do something with the metadata, you still have to receive that entire stream and process it. With 2110, we use a completely different philosophy. 2110 is a general purpose media transport over IP system. We have standards for video transport. We have standards for audio. We have standards for synchronized metadata. Each media element is carried as a separate packet stream. Video goes in one stream, one or more audio channels in another, metadata in another. You can have multiple channels of metadata, all flowing as separate packet streams. So you can imagine having a broadcast system where your color information or your image information would be on a separate packet stream from your captions, and you can combine them when you need them and process them separately when you need them. It's capable of handling a huge variety of formats. Video from standard def all the way up to 8K, high dynamic range, and beyond. Literally, you can handle video images with 32,000 pixels per line and 32,000 lines of video. So it's a huge screen, something we haven't even tried at the Olympics yet, right? It'll handle compressed and uncompressed video at any frame rate. So whether you're working at 25 or 2997 or 50 or 5997 or 100 or 120 or 240 frames per second, all those different signals can be represented in ST2110. You can have multi-channel audio at multiple sampling rates. Right now, we define it for 48 kilohertz, 96 kilohertz, and optionally 44.1. But we can also, handle other formats in the future with an extension to the standard. And then many different categories of metadata, captions, time code, anything else that you normally would put into ancillary data can be handled with 2110. So let's look at how these go over a network. So each media type goes in a separate packet stream. Makes it easy for you to process the individual components, but the signals need to be resynchronized after processing. So SDI video goes in, gets packetized. That becomes an ST2110-20 video stream. At the far end, we can depacketize that and get our SDI video back. Just the video. No ancillary data, no audio data, just the video, pixels only. The audio goes in. That's a separate packet stream. And again, we can get those audio packets back out at the far end. Metadata, again, a separate packet stream, ST2110-40 for that. We use precision time protocol to timestamp the packets so that we know when they were created. when the media in them was created, and we can resynchronize that data, those streams at the output based on those PTP timestamps. We also create SDP files for each one of the streams so that we know how to connect to them and what's inside those streams. That's a very important thing. We'll cover that in just a bit. So let's compare an audio processing packet flow between 2022-6 and 2110. This is how you'd process audio in a 2022-6 system. You'd take your video in, you would packetize it, you would route it through your network. At some point, you would have to depacketize it. You'd have to de-embed the audio, process the audio, then put it back inside of an SDI, repacketize it, and send it along to the end. With 2110, it's much simpler. We simply take the audio packets that we care about, send them to the audio processing device, process that audio, and put it back out as a new version of that audio stream. And again, we use SDP files to describe where those signals are coming from and allows receivers to connect to those sources. So we have a number of standards that have been released in 2110. There's an overview document. Anybody can download that for free. 2110-10 is system timing and definitions, and that covers a lot of the basics as far as how RTP works, and we'll get there in just a minute. Uncompressed active video is 2110-20. Traffic shaping and delivery timing. This is very important to make sure that you don't push out too many packets at the same time. Constant bitrate compressed video is 2110-22. We just did a big interop at Wuppertal at Riedel headquarters where we had many vendors sending and receiving compressed video streams using JPEG XS. PCM digital audio, uncompressed. We have AES-3 transparent transport for non-PCM audio. That's some special applications. 2110-40 for our ancillary data. And 2110-43 is a special one for TTML captions and subtitles, a special category that needed a unique way to handle the ancillary data. These are all of the released specifications in the 2110 suite. Now there's a new version of many of these coming out shortly. Of course, I've been saying that for a few months, but it should happen soon. And there's some new specs coming out as well that'll handle some more metadata formats. There's some recommended practices on how to do certain things. So it's got a lot of different flavors and capabilities in it. So 2110-20. Basically, we take video, we take groups of pixels, we call them P groups. We put a header on there. We put that inside of an RTP packet, which goes inside UDP, over IP, and then over Ethernet. So if you were capturing these packets on Wireshark, you would see all these different layers: Ethernet, IP, UDP, RTP. Then you could find a payload header and the pixel groups inside that for your video. And of course, the checksum at the end is for your Ethernet. What's a pixel group? Well, that's a good question. So the pixels are formed into groups. The size of the group depends on the sampling format, if it's 422 or 420 or 444. Whether it's 8-bit or 10-bit, all those different things affect how your P groups are made. The good news is you don't have to figure that out. It's all specified in 2110-20. You form groups of pixels that have an integer number of octets, and they all the pixels that share the same samples must be in the same P group. So if we were doing 420 8-bit video, we would have 4 luminance samples, 1 blue color difference and 1 red color difference in the same P group. 422 10-bit, which is what we use in SDI all the time, would have a blue color difference sample, 2 different luminance samples, each one of those being 10 bits, and then a red color difference sample. So those are the fundamental building blocks that we use to make our 2110-20 packets. So if you look at a video raster, the way that we represent it in SDI, the first thing that you do when you're going into 2110 is you get rid of your vertical and your horizontal ancillary data. Then all you're left with is the active video pixels, the things that are actually carrying your video image. Then we packetize that. We put it into multiple packets, and we take as many packets as we need to put every pixel of that video into a IP packet, and all those IP packets go into the same stream. We also support lossless compression. So visually lossless compression meant so that an observer can't see it. There's a number of different codecs out there. One of the most popular ones today is JPEG XS. There's a RFC for encapsulating that called 9134. We support that in 2110, but we also support other codecs like VC2. And JPEG XS and these other lossless compression typically run somewhere from 2:1 to 8:1, and you can even go higher. I'm just going to put this chart out here. We often measure lossless compression in terms of bits per pixel. What you have to remember is that SDI using 422 10-bit works out to 20 bits for each pixel that you're carrying. And if you're doing 1 bit per pixel, that means you're reducing your signal rate by a factor of 20. If you're using 3, then you're reducing it by a factor of about 7. And this chart here shows you a lot of the different bit rates for some of the very popular video formats that are out there. Now, interestingly, the bit rates are different if you use 50 hertz instead of 60 hertz. Why? Because there's fewer pixels per second in a 50 hertz frame video sequence than there is in a 60 hertz video sequence. So these numbers would go down correspondingly for 50 versus 60. So audio encapsulation. Let's not forget about audio. That's always the hardest thing, as he points to his AV system. So let's see how we would take, let's say, 4 channels of 96 kilohertz 24-bit audio and put those into packets. So we're going to put 1 millisecond worth of audio from each of our 4 channels into the same packet. Now that's not a fixed number. Sometimes you can do 1/8 of a millisecond or 125 microseconds, but our example will do 1 millisecond. So 1 millisecond at 96,000 samples per second is 96 samples. So I have to fit 96 3-byte numbers because each sample is 24 bits. 24 bits is 3 bytes. So hence you see 96 sets of 3 rectangles. Each one of those represents an individual audio sample. Now I'm going to have multiple channels. So each channel is going to have 3 bytes times 96 samples, 0 through 95, gives us 288 bytes from each channel in the packet. If I have 4 channels of audio, I'm going to have 1,152 bytes of audio data. I'm going to put that into one ST2110-30 IP packet. So because it's an IP packet, I need an IP header, I need a UDP header, I need an RTP header, and then I'm going to put my audio data in there in a round-robin fashion. So first I'm going to put in all of my number 0 samples, 1 from each of the 4 channels. Then I'm going to put in the same exact order, the channels from my number 1 sample, then my number 2 sample, all the way up to my number 95 samples. When I've done that, I've filled my entire packet, and that's ready to go out on the network. It's an IP packet full of headers and uncompressed audio samples. So we could potentially put 5 96 kilohertz channels in there, but we typically specify receivers to handle 4 channels of that in ST2110-30. We have ancillary data. We take ancillary data from the information that's already in the vertical ancillary space. We extract that, we put it into packets, and we send those packets out over the network, again with headers. Very simple process. And again, each one of these represents a separate packet stream. So let's talk a little bit about our IP transport. What does RTP give us? It gives us an M-bit that's specially used in 2110 to indicate the last packet of a video frame. If you've got 1,000 packets, it's nice to know what the last one is. The payload type tells us what's in that packet. The sequence number, that's incremented by 1 for every single packet that is in the flow, so you can keep track of them. You can figure out if packets are missing or if packets are in the wrong order. Timestamp tells you when the media inside this packet was sampled. And of course, there's some other flags and things like that which aren't really that important to the functionality of RTP. One of the cool things about 2110 is that it's based on PTP, and we're going to have a great presentation coming up next about PTP. But the important thing to understand is that with a common system clock, you can have all sorts of different media devices running all sorts of different media that reference the same clock, and each one of them can calculate its own frame sync. And every device can make the same frame sync calculation, and you end up not having to send a sync to every device. You simply give them all PTP, and they all know what they're supposed to do. It's a beautiful thing, and we have hundreds of devices out there that can do that. So all packets from one video frame will have the same RTP timestamp because they all represent the same time of sampling the video frame, but each one will have its own unique sequence number. And that's what this diagram shows. One other thing that's very important with 2110 is that we want to make sure that our signals are good network citizens. So what we want to do is we want to make sure that we don't send out our 2110 signals in a bursty manner. If I tried to combine these two signals that are on separate 10 gigabit links onto the same link, I might have a problem because I've got multiple packets arriving at the same time on different inputs, and I might overflow the buffers in my switch. So to prevent those problems, we've defined some things in SMPTE that's called packet pacing. And there's 3 different types. There's narrow linear, where the packets are spread out during the entire frame interval. We have type N, which stands for narrow. What we do is we don't send packets during the same time as the vertical ancillary space would happen. And then we have type W that's designed for wide senders and wide receivers. That's primarily to support software-intensive devices. And as you can see, the average bit rate here can fluctuate. The packets can be spaced together or farther apart. And all those are things that we support in 2110. Hitless protection switching. We send an identical signal on 2 separate pads. I mentioned this before, 2022-7. They have the same RTP timestamps and sequence numbers. I send them on 2 different IP flows. When I get to my destination, I can switch seamlessly back and forth. So if I lose a packet on path A, I can pick it up on path B. And that's a standard. And it was updated in 2019 specifically to support 2110. Here's an example of an SDP file. I won't go into the details, but if you look at this, you can tell that this has some good information about the video signal, especially down here in the FMTP parameter. You can see that this is a 422 video. It's 1920 by 1080. Again, only the video. It's interlaced. The exact frame rate is 2997, which we represent as a fraction of 30,000 divided by 1001. It's got 10 bits per sample, standard HD colorimetry, BT709, and normal standard dynamic range. The other thing that's important about here is that it has the addresses that the signal is originating from up in the top line, the O statement, as well as the multicast address that it's going out in the C line. That's important because what we do to make connections in 2110 is that we create an SDP file at the source, we communicate that to the destination devices, they each get a copy of the SDP. By reading that SDP, they can know which multicast to join, and then the network figures out how to get each one of those devices connected to the source. And we'll talk about networking in another session today. If you're interested in IPMX, there's a little comparison table. I won't go through that. There's too much detail. So why 2110? It's future-proof. We can handle any video format, 8K, high dynamic range, 3D stereoscopic, anything that we thought of we can handle with 2110. It's cloud-friendly. The IP signals travel easily to and from public and private clouds. It's flexible. We have a common network backbone. We can handle SD, HD, Ultra HD, standard dynamic range, high dynamic range, multiple frame rates, compressed, uncompressed video, streaming, file transport, and everything else on the same IP fabric. You don't have to change it out every time you change format. And one other reason, it's an Emmy Award-winning technology. So, I got time for a quick question or two if anybody has one. We will be posting this video, and I hope that folks take a look at it.